Hi student, this is Sivakumar. 11th standard mathematics chapter number 7, matrices and determinants. Already have learnt the concept of matrices. The students who have studied in state board, particularly the 10th standard. Anyway, we can recollect what we have learnt in 10th standard. Here, let's start with the matrix. A matrix is a rectangular array or arrangement of entries or elements displayed as in rows and columns put within a square bracket. Okay. Usually the matrices are denoted by capital letters A, B, C, etc. Any one of the English alphabets of capital letters. This is a general form of a matrix. If a matrix A has m rows and n columns, that is written as A that is equal to within set bracket Aij that is equal to m cross n. Both I and j, I lies from 1 to m and j lies from 1 to n. Here m cross n refers order of the matrix, m rows, n columns. Here is some example. Definition. Before that example, here look at the example of a matrix A that is equal to 2 0 minus 1 1 4 5 9 minus 8 6. These are the entries. Here this matrix has 3 rows. The horizontal representation is called a row and the vertical representation is called a column. It has 3 rows and 3 columns. So order of the matrix is 3 by 3, 3 into 3. We can call it as 3 by 3 matrix. Like that. Look at that. Here it has 3 rows and 4 columns. So order of the matrix is 3 rows, 4 columns. Here 4 rows and 3 columns. So 4 by 3 matrix. Now look at the definition. If a matrix A has m rows and n columns, then the order or size of the matrix A is defined to be m cross n. Read as m by n. So now we can discuss about the types of matrices, a row matrix, column matrix, square matrix, diagonal matrix, zero matrix, scalar matrix. We can discuss one by one. Start with the row matrix. A matrix which has only one row is called a row matrix. Look at the example here. A that is equal to 1 0 minus 1 minus 1.1 comma row 2. It has only one row. Even though it has 4 columns, it doesn't matter. It has only one row. It's an example for a row matrix. Like that, column matrix. A matrix which has only one column is called a column matrix. Look at the example here. It has only one column. Column has 4 entries, 4 elements. Even though it has only one column, it is called a column matrix. Next definition is a zero matrix. A matrix in which all the elements are zero. So another name null matrix, another name void matrix. 3 different names: zero matrix, null matrix, void matrix. It can be of any order. It is a 1 by 1 matrix. It has only one row and one column. It has 3 rows and 3 columns. It has 2 rows and 4 columns. It can be of any order. So look at that. All the entries in the matrix are zero. So these are the examples of zero matrix. Next definition is a square matrix. Square matrix in which a matrix has equal number of rows and columns. In a square, you know that sides are equal, length and breadth are equal. Like that, number of rows and number of columns are equal. We can call it as a square matrix. Look at the example. Here we have 9 elements. Here we have 9 elements. How many rows? 3 rows and 3 columns. It is an example of a square matrix. We can call it as its order of 3. In short form, we can say instead of 3 rows, 3 columns, we can call it as order of 3. Order of 3 means 3 rows, 3 columns. It is a square matrix. Right. Next definition is a diagonal matrix. Diagonal matrix is a square matrix in which all the elements are 0 except the main diagonal or leading diagonal. Look at the example here. Look at that here. 1 2 3, the main diagonal, this is called the main diagonal, leading diagonal, this is the non-leading diagonal. Main diagonal elements are non-zero numbers. At least one element has to be non-zero, then we can call it as a diagonal matrix. Other elements are zero only, right? Like that here, or yes, here these two are zero. So it is an example of a diagonal matrix. Next definition is a scalar matrix. A scalar matrix is a diagonal matrix. Scalar matrix is a diagonal matrix in which the leading diagonal elements are same. Okay, leading diagonal elements are same. Look at the example here. Root 2, root 2, root 2. Leading diagonal elements are same. Others and all 0. -5, -5. And root 3. Only a single element, that is also called a scalar matrix. Right? This is of order 3, this is of order 2, this is of order 1. Next matrix is an unit matrix. Unit matrix is a diagonal matrix in which all the leading diagonal elements are unity. Unity means 1. In general, the unit matrix is represented by the letter I. Here I1 represents order of identity matrix of order 1. It has only one element, that element is 1. I2 is an identity matrix of order 2. Here 1 1, the diagonal elements each and every one is 1, and others and all 0. Look at that. I3 represents identity matrix of order 3. Here all the leading diagonal elements are unity, 1 1 1, others and all 0. Okay, this is a general form. All the leading diagonal elements are 1, others and all 0. Okay. Next definition is upper triangular matrix. Upper triangular matrix, a square matrix is said to be an upper triangular matrix if all the elements below the main diagonals are 0. Below the main diagonals are 0, that is called upper triangular matrix. Look at the example. Here this is a diagonal elements. Look at the diagonal 4 7 2, below which all the elements are 0. This is called the upper triangular matrix. But look at the lower triangular matrix definition. A square matrix is said to be a lower triangular matrix if all the elements above the matrix, above the main diagonal are 0. Look at the example, can easily understand. Here many examples are there. Look at the first one. This is the main diagonal. Here it is. Above the main diagonal, all the 3 elements are 0 here. Okay. Here also, above the main diagonal, 3 elements are 0. Above the main diagonal, this element is 0. So, above the main diagonal, if all the elements are 0, we can call it as a lower triangular matrix. Next one is a triangular matrix. A matrix which is either upper triangular or lower triangle is called a triangular matrix. The next definition is equal matrices. Two matrices are said to be equal if they are of same order. Look at that. Here x, y, y, u. What is the order of that matrix? 2 rows, 2 columns. Even in the right hand side, the matrix of order 2 rows, 2 columns. So we can call it as equal matrices. Next, two matrices A and B are called unequal if they are of different order. At the same time, the corresponding elements are not equal. Okay, look at that example. Here 4, even though it has 2 rows 2 columns, it is also 2 rows 2 columns. We can call it as equal matrix because here 4, here 8. Different. -3 and -5, 0. Even though these two are same, 8 and 4. Others and all different. So that is an example for unequal matrices. Another example, look at the order of that left hand side matrix. It has 2 rows 2 columns, but it has 3 rows and 2 columns. So 2 different matrices, 2 different orders. So it's another example of an unequal matrices. Okay. Next, algebraic operations on matrices. We have multiplication of matrix by a scalar, addition or subtraction of two matrices and multiplication of two matrices. First one, multiplication of a matrix by a scalar. I consider a matrix A and that matrix is multiplied by K. You will be getting Ka. Look at the example here. A is a matrix here, A, B, C, D, E, F. That is multiplied by K. That means each and every element of the matrix A should be multiplied by K. You will be getting Ka, Kb, Kc, Kd, Ke and Kf. Right? That is a multiplication of a matrix by a scalar. Then negative of a matrix. If I consider a matrix A, the negative of the matrix is called minus A. So each and every element of the matrix should be multiplied by minus. That is called additive inverse of the matrix A. What it is called? Additive inverse of the matrix A. The next definition is addition and subtraction of two matrices. Addition of matrices and subtraction of matrices are possible only if the matrices of same order. Okay. Suppose matrix of order A is 2 rows 3 columns and matrix of B also 2 rows 3 columns. Then only addition and subtraction of matrices are possible. Next, multiplication of matrices. So look at the definition here. A matrix A is said to be conformable for multiplication with a matrix B if the number of columns of A is equal to the number of rows of B. So AB is possible, the matrix AB is possible only if number of columns of the matrix A should be equal to the number of rows of the matrix B. Look at that example here. In general it has been given A is of order m rows n columns and B is of order n rows p columns. So order m by n, n by p. So AB is possible, no, the condition to be satisfied, n and here n, look at that, n and n, these two are equal. This is a number of columns of the matrix A is equal to number of rows of the matrix B. Then the resultant matrix of order, the AB is of order is m rows p columns, m rows p columns. Okay. Next definition is transpose of a matrix. The transpose of a matrix is obtained by interchanging rows and columns of A, the matrix A, and is denoted by A power T, that is A transpose. Now look at the example here. I have the matrix A. For finding that A transpose, a very simple one, you have to interchange the rows and columns. I have written the first row in first column and second row in second column. That's all. This is the transpose of a matrix. Then these are some properties. A transpose of A transpose. Transpose of A transpose is A. K is a scalar here. K, A, the whole transpose equals K into A transpose. And A plus B the whole transpose, that is equal to A transpose plus B transpose. But AB the whole transpose is B transpose into A transpose, not A transpose into B transpose. B transpose into A transpose. This is a reversal law on transpose. Okay. Now for a symmetric and skew symmetric matrices. A square matrix A is said to be symmetric. The condition if A transpose and A are equal. If A transpose and A are equal, we can call it as a skew symmetric matrix. Symmetric matrix. Look at that example. Here I have the matrix A. Even if you find A transpose, you will be getting the same matrix. Because here 3 minus 6, 9. Here also 3 minus 6, 9. Second row minus 6, 8, 9. Second column also minus 6, 8, 9. Minus 6, 8, 5. And third row 9, 5, 2. Third column also 9, 5, 2. So A transpose and A are equal. Therefore it is a symmetric matrix. Next one is a skew symmetric matrix. A matrix A is said to be skew symmetric if A transpose is equal to minus A. If it is plus A, that is symmetric. If it is minus A, that is called a skew symmetric matrix. Now look at the example here. We have the matrix A. If you find A transpose, that will be equal to minus A. So it is an example of a skew symmetric matrix. So definitions, properties and all over. Now we can get into the exercise 7.1. 7.1 problem number 1. Construct your M cross N matrix, M by N matrix. In general, A that is equal to Aij, where Aij is given by, totally we have two subdivisions. We can do one by one. Okay. First you are asked to construct M rows N columns. Here M that is equal to 2 and N equals 3 is given in subdivision number 1. That means 2 rows 3 columns. 2 rows 3 columns is a general matrix. A11, A12, A13, A21, A22, A23. Look at that. How many rows? 2 rows and 3 columns. Here is the order 2 rows 3 columns. That A11 represents element which presents in first row first column. That is the meaning of A11, first row first column. Like that, A12 means first row second column, A13 first row third column, A21 means second row first column, A22 means second row second column, A23 means second row third column. Okay. First subdivision given, Aij, I represents row and j represents column. I minus 2j the whole square divided by 2. Therefore, A equals I minus 2j. Replace I and j by 1 and 1 first, because I value is 1, j value is 1. So, we can write 1 minus 2 into 1 the whole square divided by 2. Next, I and j should be replaced by 1 and 2. I value is 1 minus 2, j value is 2 whole square divided by 2. Next, I and j should be replaced by 1 and 3. I value is 1, j value is 3. 1 minus 2 into 3 the whole square divided by 2. Next, I value is 2, j value is 1. I value is 2, j value is 1. So, we'll be getting 2 minus 2 into 1 and its square divided by 2. Next, I value 2 and j value also 2. So, we'll be getting 2 minus 2 into 2 whole square divided by 2. Next, I value is 2, j value is 3. We'll be getting 2 minus 2 into 3 whole square divided by 2. Then you have to simplify, that's all. That is equal to 1 minus 2 ones are 2 whole square divided by 2. 1 minus 2 twos are 4 whole square divided by 2. 1 minus 2 threes are 6 whole square divided by 2. 2 minus 2 ones are 2 whole square divided by 2. 2 minus 2 twos are 4 whole square divided by 2. 2 minus 2 threes are 6 whole square divided by 2. That is equal to, now you can directly write 1 minus 2 that is equal to minus 1. Minus 1 whole square is 1 divided by 2. The square is only for the numerator, not for the denominator. So 1 minus 4 that is equal to minus 3. Minus 3 the whole square is 9 divided by 2. And 1 minus 6 that is equal to minus 5. Minus 5 the whole square is 25. 25 by 2. Here 2 minus 2 that is equal to 0. 0 square is 0. 0 by 2. Even you can directly write that is 0, because 0 by anything is 0. So next step you can write 2 minus 4 that is equal to minus 2. Minus 2 the whole square is 4. 4 divided by 2. 2 minus 6 that is equal to minus 4. Minus 4 whole square is 16. 16 divided by 2. That is equal to, write 1 by 2 as it is. 9 by 2 as it is. These three cannot be simplified, but 0 by anything is 0. 4 by 2 that is equal to 2, and 16 by 2 that is equal to 8. So we have completed the first subdivision. Now I proceed to that second subdivision. Here we have the second subdivision, Aij that is equal to modulus of 3i minus 4j whole divided by 4, and m equals 3 and n equals 4. Now we have to construct a matrix of order 3 rows 4 columns. So let A that is equal to 3 rows 4 columns, that is A11, A12, A13, A14, A21, A22, A23, A24, A31, 32, 33 and 34. Look at that last number 34. So 3 rows, 4 columns. 3 by 4 matrix have constructed. Since Aij that is equal to modulus of 3i minus 4j divided by 4, A that is equal to I and j should be replaced by 1 and 1 first. So modulus of 3 into 1 minus 4 into 1 whole divided by 4. Next I and j should be replaced by 1 and 2 respectively, 1 and 2. So modulus of 3 into 1 minus 4 into 2 whole divided by 4. Next I and j value 1 and 3. So modulus of 3 into 1 minus 4 into 3 divided by 4. Finally I and j values 1 and 4, that is modulus of 3 into 1 minus 4 into 4 whole divided by 4. Next I and j values 2 and 1. So write modulus of 3 into 2 minus 4 into 1 divided by 4. Then 2 and 2, that is 3 into 2 minus 4 into 2 divided by 4. Then 2 and 3, 3 into 2 minus 4 into 3 divided by 4. 3 and 4, 2 and 4, modulus of 3 into 2 minus 4 into 4 divided by 4. Next I and j value 3 and 1. So 3 and 1 means modulus of 3 into 3 minus 4 into 1 divided by 4. Next 3 and 2. 3 and 2 have tried modulus of 3 into 3 minus 4 into 2 divided by 4. 3 and 3, so modulus of 3 into 3 minus 4 into 3 divided by 4. Finally 3 and 4, so modulus of 3 into 3 minus 4 into 4 divided by 4. That is equal to modulus of 3 ones are 3, 4 ones are 4. So 3 minus 4 divided by 4. Modulus of 3 ones are 3, 4 twos are 8. So 3 minus 8 divided by 4. Modulus of 3 ones are 3, 4 threes are 12. So 3 minus 12 divided by 4. Modulus of 3 ones are 3, 4 fours are 16. So 3 minus 16 modulus divided by 4. Next 3 twos are 6, 4 ones are 4. Modulus of 6 minus 4 divided by 4. Modulus of 3 twos are 6, 4 twos are 8. 6 minus 8 divided by 4. Modulus of 3 twos are 6, 4 threes are 12. 6 minus 12 modulus divided by 4. Next 3 twos are 6, 4 fours are 16. 6 minus 16 modulus divided by 4. And 3 threes are 9, 4 ones are 4. Modulus of 9 minus 4 divided by 4. Next here 9 minus 8, modulus of 9 minus 8 whole divided by 4. Modulus of 9 minus 12. Modulus of 9 minus 12 divided by 4. Finally modulus of 9 minus 16. 9 minus 16 divided by 4. That is equal to 3 minus 4 is minus 1. Minus 1 modulus is plus 1. It is an absolute value. Modulus value cannot be negative. You have to write always positive 1. So 1 divided by 4. Like that 3 minus 8 is minus 5. Minus 5 modulus is plus 5 divided by 4. 3 minus 12 that is equal to minus 9. Minus 9 modulus is plus 9 divided by 4. 3 minus 16 that is equal to minus 13. Minus 13 modulus is plus 13 divided by 4. 6 minus 4 that is 2. 2 modulus that is 2 only divided by 4. 6 minus 8 that is minus 2. Minus 2 modulus is plus 2 divided by 4. And 6 minus 12 that is equal to minus 6. Minus 6 modulus is plus 6 divided by 4. 6 minus 16 that is equal to minus 10. Minus 10 modulus is plus 10 divided by 4. Here 9 minus 4 that is equal to 5. Modulus of 5 that is 5 divided by 4. 9 minus 8 that is equal to 1. 1 modulus is 1 divided by 4. 9 minus 12 that is equal to minus 3. Minus 3 modulus is plus 3 divided by 4. 9 minus 16 that is equal to minus 7. minus 7 modulus is plus 7 divided by 4. If it is possible, you can simplify. That is equal to, here first row nothing can be simplified, so write 1 by 4, 5 by 4, 9 by 4, 13 by 4, write as it is. 1 by 4, 5 by 4, 9 by 4 and 13 divided by 4. Second row, you know that 2 by 4 after simplification will be getting 1 by 2. Here it is also 1 by 2, 1 by 2, 1 by 2, 3 by 2, 5 by 2, 1 by 2, 1 by 2, 3 by 2, 5 by 2, 1 by 2, 1 by 2, 3 by 2 and 5 by 2. Finally here 5 by 4, 1 by 4, 3 by 4, 7 by 4, nothing can be simplified, so write as it is. 5 by 4, 1 by 4, 3 by 4, 7 by 4, 5 by 4, 1 by 4, 3 by 4 and 7 by 4. Okay, in book answer they have taken 1 by 4 as common. Before simplification they have taken 1 by 4 as common, but we have simplified here, therefore it is also correct. If you want, you can take 1 by 2 as common. It's not necessary, you can stop at this stage. Even in first subdivision, the book answer, before simplification they have taken 1 by 2 as common. Just I have simplified here, therefore it is also absolutely correct. Okay, so problem number 1 is completed, and then I'll be teaching the next problem in the next video. Thank you, children.